Hello, I'm Aniket Dada. I'm from George Mason University Robotics Lab, and we present towards field mobility on a vertically challenging terrain, platform, dataset, and algorithm. We already know most conventional robots are developed for on-road navigation, and they're quite efficient in such environment. When we use them in off-road condition, it might extend the robot reachability in many hard-to-reach environment. But such navigation capability is achieved mainly through hardware advancement, such as quadrupeds or legged robots, and active suspension or a mixture of wheeled and legged system we found on Mars rover. Due to the simplicity, cost, and availability of the wheeled platform, they possess potential to be used in many use cases such as search and rescue, remote exploration, surveillance, and navigating through rough terrain such as vertically challenging terrain. But achieving reliable and robust navigation in this environment is much more challenging due to intricate nature of the terrain, complex vehicle-terrain interaction, nonlinear vehicle dynamics, potential deformation of chassis, or a changing friction. This becomes our motivation to address this challenge for better navigation capability. So most conventional robots with existing navigation planner can only move in flat terrain. This navigation planner simply divides the robot workspace in free space and obstacle, and basically compute a path from the current robot position to the goal position, keeping robot in a free space and avoiding obstacle. But we think this approach limits the reachability in the real world. Based on this limitation, uh, we work on expanding the mobility of this platform where there is no clear distinction between what is obstacle and what is not. For example, a certain patch, a certain set of control input, and approach angle might successfully navigate robot, while others might end up in a terminal state. So our paper's contribution include three things. First is a two-wheel robot platforms, a Verti four-wheeler or V4W, and a Verti six-wheeler or V6W, which can navigate through such challenging terrain with a limited hardware modification. Second, an open source dataset which can be used by robotics community for further research and development. Third is the three benchmarking algorithms that demonstrate basic performance in terms of navigation and adaptation on a vertically challenging terrain. Here are some of the details of the Vertibilus platform. We built this robot on top of Traxxas TRX 1:10 scale crawler system, which features all-wheel drivetrain with a two-speed gearbox, front and rear differential locks with independent suspension, and a command steering. Uh, the for the RGB and depth perception, we have added Microsoft Azure camera with a pitch stabilization mechanism to extend the vertical field of view. We have a wheel speed sensor in all four wheels along with the motor for the closed loop control. As all four wheels can slip during stuck condition, we have optical flow sensors to detect the delta X, delta Y, and absolute Z. Arduino Mega handles all the low-level sensor and servo control, interfacing, and safety. The entire software stack runs on ROS Novatic and Ubuntu 20.0 for LTS. To test and experiment with a built model, we have arranged a custom test bed, which is in proportion to the robot size. It measures 3.1 meter in length, 1.3 meter in width, and 0.5 meter of elevation change. To put that in perspective, the height of the robot is 0.25 meters. As this test bed is made of multiple small rocks of various size, we can reshuffle them to create a new terrain topology. Using the platform and the testbed, we have collected an open source dataset by human teleoperation, the robot, and the recording data in ROSPAC. Each ROSPAC contains a depth and RGB image, IMU signal, joystick input, wheel RPM, and optical flow data. We have reconfigured the testbed multiple times during each data collection and took a multiple path for each configuration. We provide three baseline algorithms to demonstrate the navigational capability of the platforms and use case of the dataset. Open loop is the simplest one, which is driving robot at a constant speed. Rule-based is a finite state machine which follows the set of rules like increasing speed, backing up, and steering left and right, locking and unlocking differentials, etc. End-to-end behavior cloning uses dataset collected to train the neural net model from the human's demonstration to produce V and omega, that is throttle and steering, based on the input from the kinet. We've compared all three algorithms on the testbed with the three configurations: easy, medium, and difficult. For each test level, the configuration is fixed. We ran 10 trials of each, changing the approach for each trial. Uh, we have also did the cross deployment for the behavior cloning. That is, a model trained on V4W dataset is deployed on V6W dataset and vice versa. For the results, we report both the number of successful trials in the top two graph, where higher is better, and mean traversal time in the bottom two graphs, where lower is better. We found that in general, behavior cloning performs better than both open loop and rule-based. V6W is more stable than V4W, and the model trained on V4W dataset performs better when we deploy it on V6W, but not vice versa. Thank you for your interest in Vertibular project. If you have any question, feel free to contact us or follow the QR code for more information on the project.